So 2-1 is called inductive reasoning and conjecture. Inductive reasoning and conjecture, okay? What we do is we make something called a conjecture based on this type of reasoning called inductive reasoning. This is 2-1, yeah. What a conjecture is, okay, and we also find things on counterexamples. These are the only 3 vocab in here. These would, for example, be vocab that's on the word bank of the next test. Okay? A conjecture is an educated guess based on known information. So you're going to make a statement or a guess about what's going to happen next based on this information you know. We call that a conjecture. Okay? Inductive reasoning, which the opposite of that is deductive reasoning, which we'll talk about later. Inductive reasoning is reasoning that uses specific examples to arrive at what we call a plausible generalization, or something that's going to happen. Okay? Well, I see these examples, I see this happen, and I'm going to use inductive reasoning to say, well, since this happened, I believe this is going to happen next. Okay? And then we have a counterexample. A counterexample is a false example of a conjecture, basically proving something wrong. Okay? A counterexample saying, well, if this is true, I can prove it's not true by giving a counterexample. I'm going to show you what some counterexamples are in a second. Okay? So again, this is an inductive reasoning. In a couple chapters or sections, we'll look at deductive reasoning, which is different. But inductive reasoning, you use examples and say, based on these examples, I think this is going to happen next. Okay. Counterexample says, well, since I can do this, then that's false. Okay, that conjecture is false. So here's a sequence of numbers. Yes. So for example here, make a conjecture about the next number based on the pattern. 2, 4, 12, 48, 240. What's happening in this pattern? Get it? Anybody? What's happening in this pattern so I could get the next number? Well, to go from 2 to 4, I multiplied by 2. To go from 4 to 12, I multiplied by 3. To go from 12 to 48, I multiplied by 4. To go from here to here, I multiplied by 5. So the next number would be 240 times 6. So the next number would be 1,240. So my conjecture is the next number is 1,240. The way I got that was using inductive reasoning. I looked at these numbers, this pattern, numbers and pattern, and said, well, this is happening, so I think the next number is going to be this. That's using inductive reasoning. You guys have probably used that before. Okay? Just now you have a name for it. So we saw the pattern. We used that example to give me a next number. Okay. But that's 1440 because I multiplied wrong, didn't I? 6 times 2 is 12, plus 2 more should be 14. Sorry. Okay. But, yes, that is what the next number would be. Okay, that's a conjecture. About the next number, based on this pattern, this one's a little more difficult. Start with 1, 1/4, 1/9, 1/16, 1/25. What do we know about the denominators here of all these numbers? Well, the denominator here is 1, right? Just don't write it. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So this is going to be, right, 136. 1 over 6 squared, which is 136. That's my conjecture. Okay? My conjecture is the next number is 136 by using inductive reasoning. Okay. So here, this is a similar problem we had on the last test. For L, M, and N, from L to M is 20, M to N is 6, and L to N is 14. So if I had a line with L, M, and N, and it says from L to M is 20, from M to N is 6, and from L to N is 14. Make a conjecture and draw a figure to illustrate your conjecture. Now, this one isn't a pattern, right? I didn't get a conjecture based on a pattern here. But conjecture is just making some true statement based on what's given to you. So that's what's given to me. What's some true statement about the points L, M, and N? What's a true statement about those points? Yeah.
L minus, well, Ln minus Mn is Ln.
Yes, you could say, one conjecture you could say is wait, my picture is wrong though. Man, that's way off, isn't it? That doesn't make any sense. Sorry, Lm is the long one. Let me redraw that. Lm is 20, Mn is 6, and Ln is 14. There we go. That's 20. But yes, your idea was right. One conjecture you can make is that Ln plus Nm is equal to Lm, right? That's a true statement. Based on this example, that's a true statement. That's a conjecture. Okay? I could also say Lm minus Nm is Ln, right? That's also a true statement. Okay? Another true statement I could make based on this conjecture is that points L, N, and M are, what's that vocab word? Collinear, right? Are collinear. That's also a conjecture. That's a true statement, right? Based on this example, that's a true statement. Okay? So there's not always one right conjecture because sometimes there's a lot of true conjectures. Okay? This is true based on this example, that these are collinear, and that if I add these two pieces together, it equals the entire piece. Okay? So that's a true statement. Good. Given ACE is a right triangle, so it has a right angle. AC is the same as CE, the same length. Which figure would illustrate the conjecture? Okay, ACE is isosceles, angle C is the right angle, and AE is the hypotenuse. So I want a right triangle, which that automatically rules out D, right? That AC is the same as CE, okay, and that AE is the hypotenuse, or the angle opposite the large angle, and angle C is the right angle. That would be C, right? Angle C is the right angle, AC is the same as CE, and AE is the hypotenuse. Okay? So they gave us that conjecture there and just had us match up the figure. Now finding a counterexample. So counterexample, I give you something, I give you a conjecture, you tell me a way that conjecture is false. So given that AB is the same length as BC, remember they used the equal sign since we didn't put the segment bar over the top of it. That means their measures are the same. Like if one of them's 5 inches, the other one's 5 inches. If I would have wrote something like this, I would have put congruent, right? When you use the segment bar, you use congruent. When you don't use the segment bar, you're just talking about the actual numerical length. It's equal. Okay? So if I say, given AB is the same length as BC, the conjecture is B is the midpoint of AC. I want a counterexample so that this is true, but the conjecture is false. That's what a counterexample is. The given is true, but the conjecture is false. Can we think of a picture or a way we can do it so that the given is true, but the conjecture is false? I want AB to be the same as BE, but this needs to be true, and this needs to be false. What if I did this? And called this A, B, C, and those were the same. Is my given true? Yeah, AB is the same as BC, and let's say I said it was, okay, 4 feet, this is 4 feet. Is my conjecture false? Is B the midpoint of AC? It's not, right? The midpoint means like I have a line here, and A, B, C, the midpoint, these two pieces would be the same. But that's not, right? My given is true, but my conjecture is false. This is a counterexample. Okay? This is a counterexample, yes.
Wait, why was it true whenever you didn't have the 4 feet on there? But now that you put the 4 feet on, now you're saying it's not true.
No, it is true. I just added that 4 feet.
Okay.
It is true. This is still true, right? The length AB, which is 4 feet, is the same as the length BC. That's also what these tick marks mean, right? Okay. But the conjecture is false. B is not the midpoint of AC. Right? This is true. This is false. That's a counterexample. Okay. So in one part of these, you have to find a counterexample to this given if the conjecture is this. Most of the time, you just have to find a figure or a way that that doesn't work. Okay. Find a counterexample for this. I want you to think about this one yourself first. Given if the product, so that's multiplication, of two numbers is even, conjecture is both numbers must be even. So can you find a counterexample? So give me an example where the given part is true, two numbers multiplied together is even, the conjecture, both numbers are even. Like for example, this would not work. 2 times 2 is not a counterexample, right? It works for this, the product of two numbers is even, but both numbers must be even. Well, that's also true. This is a true statement that follows the conjecture. I want a counterexample. So I want some example that works for this that doesn't work for the conjecture. A few people have it. I'll give a few others a chance to think here. Can you think of a conjecture or a counterexample that makes the conjecture false?
5, 2.
Right. 5 times 2 is 10. That's a counterexample, right? Because the product of these two numbers is even. 10's an even number. But both numbers aren't even. 5's an odd number. This is a good counterexample. What's another one? 3 times 4 is 12. Both numbers are even, but, one number is even, one is odd, but their product is even. What's another one? Yeah, Brittany. 1 times 2. Their product is even, one number is even, one number is odd. Okay, those are good counterexamples. Like I said, oftentimes there's a bunch of different counterexamples. The conjecture has to be false, the given has to be true. Okay. Oh yeah, then I got some riddles for us to look at today for some reasoning.